All right, so we're just going to do a quick overview of the examples that we went through with trigonometric identities in class, just in case any of you need a refresher or you were out and are preparing for an upcoming assessment. So we actually started on page 2 of the notes packet, remember? And we talked about how we can combine the trig expressions of sine and cosine, remembering our definitions of SOHCAHTOA here. We are able to take, if we combine like the opposite divided by the hypotenuse, divided by the adjacent divided by the hypotenuse. Remember, a fraction divided by a fraction gets changed, and flipped. And so what we have is opposite over hypotenuse times hypotenuse over adjacent, and then the hypotenuses cancel out. And so that allows us to know that sine over cosine, or opposite over hypotenuse being sine, cosine being adjacent over hypotenuse, is giving us opposite over adjacent or tangent. So these are two important fundamental ratios that we want to keep in mind. Sine over cosine is the same thing as tangent, and notice that's an identity, so that means the logic could go, I see this ratio and I substitute tangent in, or I see tangent and I move it back to its pieces of sine and cosine. The same is also true about the cotangent ratio, remember? We can take the reciprocal there, cosine over sine, and have that be the same as cotangent, or we can see cotangent and plug in cosine over sine as a result. Okay, so those are fundamental identities we want to keep in mind in addition to what we're about to do, which is the Pythagorean identities. Okay, now here back at the front of our packet, we're going to be developing a Pythagorean identity that goes along with trigonometry. So we're looking at our unit circle picture here, and we have our right triangle that's in shaded area here, and we're recalling that any point on the coordinates for the unit circle always has the x-coordinate is cosine and the y-coordinate is sine. So if we thought about like labeling our sides A, B, and C here, A would be the vertical component of that point right there, which is the sine of this angle, theta, and the horizontal component, B here, would be the same as cosine, okay? So what we're going to be able to substitute in is that A is the same as sine, and B is the same as cosine, where C, because it is the unit circle, C is always going to be 1. So we have sine of theta squared plus cosine of theta squared is going to equal 1. That is what we call a fundamental Pythagorean identity. Okay, so what we need to do is that we're going to actually tweak the notation on that and kind of get rid of some of the parentheses and some of the clutter of how we would write it. And so instead of sine of theta in parentheses all squared, you're going to see sine squared theta. Same thing with cosine. Instead of cosine of theta in parentheses all squared, we're cleaning that up to cosine squared theta. And that's always, of course, equal to 1. So that's, again, known as our Pythagorean identity. The next thing we're going to do is we're going to see if we can develop other identities from that one sine squared plus cosine squared equals 1, because it would be good if we could use all 6 of the trig ratios, not just sine and cosine. So the first thing we're going to do here is we're going to take sine squared plus cosine squared equals 1 and rewrite it, but then we're going to divide each side of the identity that we just wrote in number 1 by sine squared theta. So that means each side, actually there's 2 terms on the left-hand side and 1 on the right, so we're actually dividing it in 3 locations. Sine squared over sine squared equals 1. We're going to remember that we just developed a ratio here for cosine over sine, and cosine over sine is cotangent, so we're going to have 1 plus cotangent squared theta, and then 1 over sine squared theta. Well, that's our reciprocal identity for sine, or cosecant squared theta. So there's a second Pythagorean identity, all still coming from this sine squared plus cosine squared equals 1. Then we're going to, I think you can probably guess, take that same Pythagorean identity, and we're going to divide it by cosine squared, and we get sine squared over cosine squared, or tangent squared, and then cosine squared over cosine squared, or 1, and then that's going to equal 1 over cosine squared, or secant squared. Okay? So those are our 3 Pythagorean identities. Let's go to the next slide and talk about how we would actually use those to start simplifying these trigonometric expressions. At the top of the back part of the first page, this is example 2. It does come from your textbook. Remember, what we want to do is we want to simplify the identity, and so we're going to start by factoring out the common factor of sine. If we take a sine out of this first term here, glued together with multiplication, and the second term, then we're left with cosine squared x minus 1 in parentheses. Off to the side, you can see this calculation here. I would like to substitute in for cosine squared x minus 1 for something from the Pythagorean identity. Well, in order to get cosine squared x minus 1 alone out of this identity, I've got to move my 1 here over to the left-hand side, and then I need to move my sine squared over to the right. So when I do that, I get that cosine squared x minus 1 is equal to a negative sine squared x, moving the terms in that identity around from side to side. Then remember, this is still glued together with multiplication, so that's sine times negative sine squared, or negative sine cubed x, and that's the simplification there. The next example, we're going to pull out again the common factor. We see a tangent squared in both terms. This first term is itself, and then the second term it's glued to a sine squared x. So if I pull out a tangent squared x, I would have 1 minus sine squared x. Remember our discussion that whatever's in the parentheses should have the same number of terms as what I started with. This is 1, 2 terms here, so 1, 2 terms in the parentheses. Now I hope you can see the substitution that again we want to make for 1 minus sine squared x. If we take our identity, sine squared plus cosine squared equals 1, and we move sine this time so that it's 1 minus sine squared, that just leaves us with cosine squared there by itself. So that's the substitution we want to make with Pythagorean theorem. And then notice tangent squared can be rewritten because we have a cosine in the numerator. Sine squared over cosine squared is equal to tangent, just like we saw on our first discussion page here. So we have cosines canceling out, and we just have sine squared x is what that whole expression is able to simplify to. All right, let's go to the next page. We're going to use the basic identities this time to simplify, because sometimes we do not yet see at the beginning any of the Pythagorean identities that kind of jump out at us. The Pythagorean identities jump out at us when we have a 1 and a squared of any of the 6 ratios kind of on the page looking at us. What we don't have yet, though, is a squared. So let's see what we can do with example 5 here from page 376 in your book. A good simplification strategy when you don't see Pythagorean theorem is to rewrite everything in terms of sine or cosine. Okay? Remember, sine and cosine are the building blocks of everything else. The reciprocal of sine is cosecant. The reciprocal of cosine is secant. Tangent itself is built sine over cosine, and cotangent is built cosine over sine. So if I can write everything else out in terms of sine and cosine, then probably some Pythagorean identities are going to start coming through. So here we have sine. We don't need to rewrite that. Cotangent, though, it might be helpful for us to rewrite. So we'll write that as cosine t over sine t times cosine t. That doesn't need to be changed. But when I simplify that, I get sine t plus cosine squared t over sine t. Now, this is not yet able to be added because this is a number without a denominator and a fraction with a denominator. So I'm going to get a common denominator of sine t by multiplying numerator and denominator of this first term by that exact expression, sine t. And so we actually get sine squared t over sine plus cosine squared t over sine. Now that we have a common denominator, we can put them together, and we get sine squared t plus cosine squared t in the numerator, which we know has an identity of 1. And I'm just going to underline here because we have another Pythagorean substitution. Sometimes it helps to focus on where that is in the problem. And then our final simplification, you guys, is 1 over sine does equal cosecant. Let's see what we can do with the next example. We have sine plus cosine of x all squared. So my advice to you whenever you have a binomial squared is to rewrite it side by side so that you can see FOIL of FOIL coming out of that. Sine squared plus sine times cosine plus another sine times cosine. That comes from the inner and the outer, or the oi, like we like to say, of FOIL. And then the L of FOIL is cosine times cosine, or cosine squared. In the next step of simplification, we're finding that sine squared here and cosine squared here are simply going to combine to 1. And where we have sine times cosine and then another sine times cosine, that actually does not simplify each of those terms, but they are like terms because they're the same two quantities multiplied. So instead of 1 sine times cosine x plus another 1 sine of x times cosine x, we actually get 2 of those same expressions. And so our simplified answer finally is 1 from the sine squared plus cosine squared plus 2 times sine of x times cosine x. Okay? Moving along, if we keep on using the idea of how to get and add those trig expressions, of course we want to get a common denominator. So for the first problem, we don't have a common denominator yet. So notice the step that we want to do is multiply numerator and denominator by whatever factors are missing in the common denominator being the product of the two denominators to begin with. So on this left fraction, I need to multiply by sine over sine, and on the right fraction, I need to multiply by 1 plus cosine over 1 plus cosine. And notice when we distribute here our cosine into this whole entire factor, we get cosine theta plus cosine squared theta. Of course, we get sine squared over here. But again, we see our Pythagorean substitution, those two pieces right there, as we merge the denominators, coming together to be 1. So we just have 1 plus cosine of theta in the numerator over the denominator, which is the product of sine times 1 plus cosine theta. Well, notice that whole entire numerator is going to go away with that factor in the denominator. And so I just have 1 over sine, or cosecant. Yes, all of this nastiness just does become cosecant. Seems a little evil, but you can handle it. Moving on. Second example here, if we go ahead and again find a common denominator, multiplying the 1 plus cosine, numerator and denominator by the other denominator, 1 minus cosine, and vice versa. We of course get 1 minus cosine squared in each denominator, and then each numerator basically becomes the other denominator. So 1 minus cosine of x, since that's what I had to multiply 1 by here, and plus 1 plus cosine of x, since that's what I had to multiply this 1 by in the second fraction. Notice the cosines are going to cancel out, but that's just going to leave the 2's. So 2 over sine squared x is 2 cosecant squared x, remember, because sine is in the denominator there, and so it's a reciprocal function. And in our next example here, example 7, we're going to rewrite this whole expression without fractions. So we're going to rewrite 1 over 1 plus sine of x so that it's not in fraction form. So normally when we rewrite something not in fraction form, it's usually in the case of, like, let's say you're simplifying a equation and putting it into slope-intercept form, and so like maybe somewhere along the way you have a situation like 3y equals negative 2x plus 9, and you want to simplify that and get y alone, we would be dividing the entire side by 3, which, remember, we would change to y equals negative 2/3 x plus 3, because we actually divided that 3 into 2 terms in the numerator, right? Common denominator divisor here goes into this first term and into this second to be simplified correctly. Well, we actually have the opposite of that going on here at the beginning of this trig expression. We have 2 terms in the denominator, and we cannot do the same algebra. We can't divide the numerator over each denominator. It doesn't work that way. So what we want to do so that it's not in fraction form is we want to multiply by what's called the conjugate. And I've rewritten that for you down here too, so we must know it's really important. The conjugate is simply the same denominator, only instead of a plus sign, we have a minus sign between the 2 terms. So we're going to multiply by the conjugate in the numerator and in the denominator. Otherwise, we've changed the value of the expression. This whole thing really just being equal to 1, remember. So 1 times 1 minus sign is 1 minus sign, but 1 plus sign times 1 minus sign is 1 minus sign squared. Now you might say, Mrs. Pollack, how is that easier? Well, it's not yet because we don't have one term in the denominator. However, when we make our Pythagorean substitution for 1 minus sine squared and it becomes cosine squared, now we have the right situation. We have a common one-term denominator that can be divided into the 1 and divided into the sine. So 1 over cosine squared is secant, and then sine of x over cosine squared can be written, as you can see here, sine over cosine times cosine, and so this part can be pulled off. The sine over cosine can become our tangent, and then I have cosine still left in the denominator, so that's like 1 over cosine or secant. So my final answer is secant squared minus tangent x times secant x. Final example, you can see we have sine squared to begin with over 1 minus cosine y. We want to start by multiplying by our conjugate here, 1 plus cosine of y. And we're going to go ahead and do that. We get 1 minus cosine squared y in the denominator, which of course we can make a substitution for, which is sine squared. And then this one's actually even a little bit more straightforward because the sine squared denominator that was, or numerator that was there to begin with, is going to cancel with the denominator we just substituted, Pythagorean substitution underlined there, and we just have 1 plus cosine y left. And on our final page of notes here, we're going to talk about identities for cofunction identities, and the cofunction identities are the ones that are seen between relationships of an angle and its complement. So CO is reminding us of the idea of complementary angles, which from geometry, remember, are the angles that add up to 90. So complementary or cofunction identities, keep that in mind. We're looking at a very simple right triangle here. We've labeled the sides 3, 4, 5, and we're going to find all of the 6 ratios sitting at different points in the triangle each time. So, for filling in this table, sine of theta puts us right here in this bottom left-hand corner angle. Sine is 3/5. Cosine is adjacent, so 4/5. Tangent is 3/4. And then we're filling in the rest. Cotangent is 4/3, secant is 5/4, and cosecant is 5/3. Then, for this third column of the table, we are filling in and sitting at the other angle in the right triangle, or the complementary angle. So that's this top corner, 90 minus theta. And we see that if we sit in the other spot, some things are kind of moved around. Now sine is actually 4/5. Cosine is 3/5, so they've kind of swapped places. Tangent is 4/3, which is what cotangent was before. and cotangent is now 3/4, which is what tangent was before. Secant is now 5/4, 5/3, and your cosecant is 5/4. So those have also swapped places. So you can see the cofunction identities at the bottom here, again, are going to relate an angle to its complement, and so we could see that as 90 minus theta, or we could possibly see that as pi over 2 minus theta in one of our simplification examples. And we're going to, as you can see, we kind of drew lines here between the ones that matched up, right? So the ones that match up are that if I'm looking for the sine of 90 minus theta, the sine of 90 minus theta is 4/5. Well, that traces actually back to the cosine of theta. And so you can see those relationships there, and vice versa, and tangent and cotangent, and secant and cosecant. So that is why they have had those names that we've been kind of confused about all along. Hopefully you can understand that idea of cofunction identity and be able to apply it when it comes to your homework. That is a general overview of all of the notes that we talked about before we are ready for our Trig simplification of expressions quiz, and I hope that was a good refresher for you guys.